let's start. So we're going to continue from last lecture. So last lecture was intentionally pretty low-key in terms of the topics we were covering because we had a midterm on Tuesday night. That's now done. We will sort of get back into full speed. So just a quick announcement, just to make sure everyone remembers. Homework 6 is out. Probably people didn't look at it on Monday. That's okay. But homework 6 has a few questions on error correcting codes, so because you haven't really had homework on that yet. And it's light on purpose so that you have time to do the midterm redo. So the midterm has been posted. We'll create Piazza threads if they haven't been created for every problem already. You can discuss there. You can treat it like homework. Overall, homework should be light this week, even if you include the midterm redo, because the midterm was a 2-hour exam. So redoing it should, on par. But if something you didn't understand, make sure you understand it. Go through the midterm redo, do it from scratch, every part of every problem. Submit that. We will then release solutions to it. Once we release solutions, you can self-grade your midterm redo to make sure you understand the solutions and what you did. We're not going to ask you to turn in a midterm redo, but this is strongly encouraged, as for the same reason that it's always encouraged. Anything that you did not get right after having time, you should read the solutions, put the solutions away, make sure you can do it right. Okay? Otherwise, you'll have a hole in your understanding, and this is not a class which is very compatible with having holes in your understanding. It will hurt you later. Hopefully, the goal of all this is, by the time you have done all this, you will understand the material in the midterm. Once you have submitted your self-grades for the midterm, we will release the exams you did in the designated rooms. We'll release those scans on GradeScope for you, so you can see, how we had graded that attempt. By that point, hopefully, you already will understand what the right answers are for everything, and you can also help us catch any bugs in our grading, because we're trying, but probably there might be some mistakes. We're going to count on you to help us fix those mistakes. There'll be rubrics and so on. We'll talk more about that right before we release. Okay, so that's the announcement. The material we're going to be going into is material from Note 11, which should definitely be up. It should have been up on Tuesday, but definitely should be up. I can understand if people really haven't had a chance to read it with the midterm and all, but you probably should. We're not going to talk about everything in lecture that's in the notes. I'm going to try to hit highlights. But Note 11 introduces the idea of counting and how do you count, kind of strategies for counting, how do you think about it. And it introduces a new kind of proof technique, which is a kind of proof by stories. And these are called combinatorial proofs. And they're very important, and they really do represent a distinct kind of proof from the ones you've seen so far. So most people have probably had some exposure to basic counting before. I know it's part of standard curricula and so on for K through 12. But last time we kind of went through in a way, kind of review and also kind of putting things into our language. And last time we talked about how there's essentially 3 major rules of counting that we use. There's the 0th rule, which you sometimes forget, is what does it even mean to count something? And what it means to count something is to put it into one-to-one and onto relationship with the finite set 1 through something. So what it means for there to be 5 sheep is that you can go 1, 2, 3, 4, 5 sheep, right? And it's like the 0th rule of counting, which means if you can put something into one-to-one association with the appropriate subset of the integers, you've counted it. Now, the more useful thing for counting, instead of counting one by one, is this multiplication rule, which we talked about last time, which is just that if you have groups that have the same amount of things in them, and you have some number of those groups, the number of things you have is the number of groups times the number of things in each group. Then we talked about the idea of the division rule, which is, that's multiplication. Addition is easy. Where does division come about? Division comes about when you have something you kind of don't care about. So you have 15 things, you have groups, each group has 3 things in it. How many groups do you have? 5. Right? 15 divided by 3. So that's what we talked about last time. And we use this for certain examples. So I'm just going to put the examples on this side as examples that you should instantly see. If you want to count the number of binary strings of length n, that's 2 to the n. Why? Multiplication rule. 2 times 2 times 2 times 2. How many times? N times. N factorial, we did last time, is the number of ways of arranging n distinct objects in a line. So in order. Why? You have n choices for the first thing, times n minus 1 choices for the second thing, times n minus 2 choices for the third thing, and so on. Then we said, if you only want to arrange k out of these n objects into a line, then you have n factorial divided by n minus k factorial. And there's a couple of different ways of thinking about that we talked about last time. Then we moved on to say, suppose you didn't care about the order. Now we're using the division rule in a more substantive way. Then, if you want a number of ways of picking k out of n distinct objects, where you don't care about the order in which you pick these k, just that we have k of them, that is n choose k, which is n factorial divided by n minus k factorial. So that's the number of ways of arranging k out of n distinct objects in a line, where we care about the order, and then we don't care about the order. So how many different ways are there to order those k objects? K factorial. So the number of ways when you don't care about the order is the number of ways when you do care about the order divided by the number of ways to order. But this division rule is only valid in the case when every single thing that's equivalent has the same number of things in it. Okay, so this is last time. So what we're going to do now is we're going to move on to talk about more advanced things that we can do, and in particular would be ideas around combinatorial proofs, which are like proofs by stories. So it's actually easy, I think it's easier to understand the idea of combinatorial proofs and the idea of by story when we just think about counting something. Right? Don't worry about it as a proof, just think about a strategy for counting. So the example we're going to do is a classic example for this. So you look at this, and you see that you always have this word here, distinct. Distinct. Distinct objects. And sometimes you have objects that are not distinct. Okay? So it might be that to an incredible lover of grapes, each individual grape is distinct, but perhaps to you, all green grapes are green grapes. Okay? And so you don't really think of the green grapes as being distinct. As an example, objects that are not distinct. So, how can we count the number of ways of sort of picking things out when the objects are, not distinguishable? The objects themselves are not distinguishable. So, an example of this, if you want to think of it, is you would like to put toppings on your yogurt. Okay? So you have some frozen yogurt, you want to put toppings on it. And you get to take n toppings. But the toppings here are the individual objects of the toppings. Okay? So this particular place says you can take n things. So that can be a chocolate chip, like one chip. Okay? Or it could be a grape or a raisin. Okay? So suppose you had chocolate chips, grapes, and raisins. So we'll call this k equals 3 kinds of things. The individual raisins are not distinguishable to you, the individual chocolate chips are not distinguishable to you, nor the individual grapes. So when you say you get to take n toppings, the question is, how many ways can you take them? So an example here would be, you could say, I will take n chocolate chips, 0 grapes, and 0 raisins. This is one such way. You could take n minus 2 chocolate chips, 1 grape, and 1 raisin. That's also a way. Does everyone understand the question of what we're trying to count? Okay. So when you look at this counting question, I'll go to another page here. Okay? So that's the counting question we have. And if you try to count it using the kind of division rule strategy, you come up with you encounter a fundamental obstacle. And the obstacle is, if you think about, well, let me pretend that I don't care about, I'll first count the number of ways of picking distinct grapes and distinct raisins and distinct chocolate chips. The thing is that the number of ways of arranging them is going to be different depending on what these counts end up being. Okay? So you can't divide by that because there's going to be different numbers. Remember, you can only use a division the rule when every grouping has the same number of things in it. And so you're kind of stuck. Okay? You don't know what you can do. So in these kinds of situations is where an element of creativity is required and an element of practice, lots of practice is required. Where what you need to do is to ask, instead of counting this way, is there another way that I can count this? So is there another story I can write, I can tell? So in this particular case, you can sort of come up with a story by drawing some pictures. So in this particular case, you say, okay, let me try to visualize what's going on. So I'm going to add more detail. So this is like an interesting thing. Usually, when you're trying to solve problems, you're usually in the process of removing detail. But in combinatorial proof, sometimes you want to add detail because you want to see if there's some other story you can come up with. So you say that, I'm going to this yogurt place and to pick these n toppings. How are they going to tell that I have n of them? And how am I going to how should I go to the checkout counter, right, to check out my toppings? I need more visual detail, right? So you say, okay, maybe what I'm going to have is I'm going to have a tray. Okay, my tray. And in my tray, I'm going to have to arrange my grapes over here. There'll be a grape section. And then, there'll be some kind of thing which demarcates the end of the grape section. And then there'll be the chocolate chip section. And then there'll be some kind of demarcator, so some little chocolate chips of some kind. Then there'll be a demarcator, and then there'll be the raisin section. You can put, your raisins in the raisin section. And then you'll take this tray, and you'll go check it out, and they'll count the number of objects in here, and make sure you have n of them. Everyone see? We're trying to add detail. So you ask yourself, okay, so I have these different sections. How can I think about this? How would I make the counting machine that counts this? Maybe they want to automate this. So you take this tray. Maybe I could have particular slots in which you have to put the grapes, the raisins, and the chocolate chips. So it's you just run it in the machine and they can just tell that every single slot is filled. Maybe underneath the slots there will be a little tiny spring that will just get set off by putting the weight of a grape or a raisin or a chocolate chip, right? And it'll make electrical contact. And then I can just see that they all light up, right? This is insane adding detail, right? But you're trying to sort of explore this question to see if there's something that can make it more concrete. So you think, okay, with slots. And then you say, maybe at some point this store is going to want to offer, a special deal on raisins. So they want to make sure I don't mix the raisins up. I better have the raisin section be clear. So I'm going to need these things that I put in. And then you wonder, wait, now I have a question, right? If I have these standardized slots, then where do I put the raisin divider? And where do I put the chocolate chip divider? Okay? Do people see? So you think, okay, how can I engineer this thing, right? I'm going to have to put the chocolate chip divider somewhere and the raisin divider somewhere. So how many slots do I need in my tray? Okay? Maybe it would be easier to be able to put these dividers in the same slot that I would put a raisin or a chocolate chip. People get the spirit of this? We're kind of using, what? You just wanted to count this thing. This is an example. Why are you obsessing about the engineering design of this, tray? Okay? And the reason is, it's helping us think about what our freedom actually is. Right? Because counting is about seeing how much freedom you have. So the engineering design process is also understanding how much freedom you have. So it's not unrelated. So then we think, how many slots do I need? I'll have n for actual things plus 2 slots. Because I need to put these 2 dividers somewhere. Now, if I choose to take no raisins at all, I could just put the raisin divider at the end. Does everyone see that? So I'm not losing anything by having n plus 2 slots. And I force you to put these slots in. So again, counting is about understanding how much freedom you have. Anytime you can constrain that freedom without changing the count, without changing the essential nature, that's good for you. Okay? So then you think, okay, now let's revisit the question. How many ways are there to take n toppings between chocolate chips, grapes, and raisins? And you can see that if this is the grape section, and this is the chocolate chip section, and this is the raisin section, that the position of these 2 dividers will tell me exactly what's everywhere. Does everyone see that? It's all the freedom I have. If I wanted to, I could be the person with their personal assistant and say, I won't deign to touch these things, divider, divider. Now you, minion, go get me things. And the minion will go and fill in the grapes and the chocolate chips and the raisins and take it to the counter and then bring it to you. Right? So, all you need to know is the position of the dividers. And so, now we can count it. How many choices do I have for where do I place the dividers? Well, how many places could I put them? Right? I could put the dividers in n plus 2 slots. I have to choose 2 slots. So the answer is instant. N plus 2, choose 2 ways. Yeah, question. So great. The question was, I want to have the grape section be the first section, the chocolate chip section be the second section, and the raisin section be the third section. So I'm going to say these dividers are just dividers. I don't have the divider that is closest to this side is the raisin divider. It doesn't say raisins on it. Okay, everyone knows the raisins go at the end. So, but now what I did was I converted this problem of counting the ways to take chocolate chips, grapes, and raisins, and I turned it into how do I count ways to place 2 dividers in n plus 2 slots, which is the same as ways to pick 2 slots out of n plus 2 slots. So I made it into this case by changing the story. Yeah. Why is it n plus 2 slots and not? So here's the divider. Here's the divider. It goes into a slot, and I need n grapes plus chocolate chips plus raisins. So I need n slots for the actual toppings, and I need 2 slots for the dividers. So that's why there's n plus 2 total slots. Okay, so this is a way of counting by coming up with an alternative story. So instead of trying to bash my head into figuring out how to count this thing, I said, let me tell a story about the tray, figured out something about the tray, and realized that this count is identical to another count. How do I pick 2 slots out of n plus 2 slots? And so I can answer it in general, right? In general, it's going to be n plus k minus 1, choose k minus 1. Why? Because I have k minus 1 dividers, because I have k categories, and I have n things that I'm going to choose. So I need n plus k minus 1 slots, and I choose k minus 1 of them for the dividers. So this is the heart of the idea of combinatorial proofs. It's really this combinatorial thinking which is changing the story. So this kind of thinking of changing the story plays a role analogous to change of variables. When you're solving differential equations or thinking about systems of equations or any kind of thing, right? In general, you want to count something in its easiest place to count it. And so that's going to involve changing stories. Same way you want to solve differential equations in the easiest coordinate system to solve them. So in this case, we said that even though our question was about chocolate chips, grapes, and raisins, it was easier to think about slots. So that was the right kind of way of thinking about it. So we're kind of lifting everything up in our minds. So this is a way of doing this. Now, why do we call them combinatorial proofs? We call them combinatorial proofs because this kind of thinking is often used to prove certain kinds of identities. So an example of such an identity is, these are just classics, and I think these are all in the notes. So here's a classic. 2 to the n, should keep this visible. Okay, 2 to the n is the same as the sum I equals 0 to n of n choose I. So, prove this. How do you prove this? So the way you prove this is you say, can I come up with 2 different ways of counting the same thing, such that one of those ways of counting will give me 2 to the n, and the other way of counting will give me this. If I can have 2 different ways of counting the same thing, the counts have to agree. If I can simply come up with 2 stories of how to count the same thing, I'm done, as long as I can get them to agree. So here, it's easy. You say 2 to the n. This is the number of binary strings of length n. So then the question is, how else can I count the number of binary strings of length n? I can think about the number of binary strings of length n by how many ones they have. I can group it into groups. This is like grouping, adding things up. Into groups by how many ones they have. So the binary strings of length n will have somewhere between 0 and n ones. How many binary strings are there that have 0 ones? It's the number of ways of choosing 0 positions in the string to call ones. So it's the same kind of position thinking. Okay? So n choose I is number of n length binary strings with exactly I ones. Why? Because I can choose the I positions for the ones. Once I choose the I positions for the ones, I know the string, because the rest are zeros. And there's n distinct positions. So this is an example of a combinatorial identity, proven using a combinatorial proof. So here, look at what happened. We had a particular set of things we were counting, binary strings, all binary strings of length n. We counted it in two different ways. We counted them directly by how many choices you had for the first position, second position, and so on, using the multiplication rule. Then we divided it into equivalence classes, which were by the number of ones they had. Then, to count each of the individual equivalence classes, we changed the story again. A small change, but a change nonetheless. Instead of thinking of the binary string as a binary string, we thought of it as a bunch of slots that could be filled with zeros and ones. And we asked where we put the ones. So we changed the story kind of twice. Once to divide the two different ways of counting, and then another way to count this individual thing. Any questions on this identity? So what you want to do when you're doing these, and we're going to give you some homework that has practice, we're going to sometimes tell you stories. We'll tell you, prove this identity, here's a story. To get you some practice, like using the stories to write these proofs out. Eventually, you're going to have to come up with these stories on your own. And that means look, think about the things you know how to do and try, and you'll be frustrated. And everyone is, and you have to learn how to do it by practice. Counting can become arbitrarily hard. So counting is an area where if you try to think of questions, it's very easy to come up with questions that you can't count. That's okay. Entire courses could be taught just on counting. So we're just not going to go that far. So let me do another combinatorial identity. So here's another one, another classic. And we'll make you prove many of these. N choose k plus 1 equals the sum I equals 1, n minus k, n minus I choose k. So this is another identity. So you have to come up with stories. So when you're coming up with a story, in this case, it's probably easier to come up with a story for this side to start with. So this story is choose k plus 1 somethings out of n somethings. Okay? Like you can see, this is n choose k plus 1, so it's going to be something of this type. So now the question is, these n things, what do you want to make these n things for choosing? So a default choice for n things, in this case, could just be the integers 1, 2, 3, 4, 5, 6, 7, 8, 9, all up to n. Why might you want to do that? You might want to do that because on this side you have a sum, and you notice that you have a k plus 1 here, so you're choosing k plus 1 things here, and here each of these things is choosing k. When you see something like this, you might think maybe this is a story about a way that you choose. Okay? some particular way that you choose. And it feels like recursive. Somehow, from here to here, you've chosen one thing. You have k plus 1 things you wanted to choose here, and here is some story of you choose one, and then you have to choose the k. So, you say n out of first n natural numbers starting at 1. Why? Because I have a 1 here. Okay, so now I picked a story for this side. You can have to change the story. It's totally natural to have to change the story, but in the interest of time, I will choose a story that works. So now you have to ask yourself, what is I? What's I? Right? In your story on this side, what is I? So maybe I is the first number you chose. Okay? And maybe we're going to say you have to choose these k plus 1 numbers, and you have to pick the smallest number first, and then pick a next bigger number, and then a next bigger number, and so on. Totally reasonable. If you want to choose k plus 1 numbers out of 1 through n, you're free to choose them smallest to largest. Right? Anytime you chose a collection, you can certainly order it. So you can think of it that way. So you ask yourself, what's I? I is the smallest number chosen. So why is it that we're taking the sum to n minus k? Because I have to choose k plus 1 numbers. The smallest number can't be, like, n minus k is as small as it can get. Right? Like, think of k equals 1. Right? I mean, like, that's, you have to pick that number. So, if you think about this case, then what you're doing is, k equals 1 means you're picking 2 numbers, right? If you're going to pick 2 numbers, the smallest number has to be n minus 1 at least, because you could pick n. Otherwise, if you picked n as the smallest number, like, where's the second number? Okay, just make sure everyone understands this. So once you've done this, you can interpret this. N minus I is numbers left to choose from. How many? So if you happen to choose 1 as your smallest number, then you have n minus 1 numbers left to choose from. If you chose n minus 3 as your smallest number, then you're just going to have n minus 2, n minus 1, and n left to choose from. So n minus I will tell you how many numbers are left to choose from. How many do you have to choose? K. Does everyone see? And this is the proof. We've counted the same thing. How many ways are there to choose k plus 1 numbers out of the first n natural numbers? There's n choose k plus 1 ways to do that. I can also choose to choose them in this particular way. I will first choose the smallest number in my collection, and then I'll choose the rest. How many ways are there to do that? How many ways are there to choose the smallest number? Well, there's all these possibilities for the smallest number. Each of them has a different amount of ways that you can choose the rest. Okay, add them up. Done. This is the combinatorial proof. 2 different ways of counting the same thing. Okay. Any questions on these? There are more examples in the notes. What I want to do next is to do an example that is not in the notes. And this is an example that is at a level of complexity that is beyond anything that we will ever ask you to do on your own. But it's nice to show you some of the spirit of this kind of combinatorial thinking, because there's lots of movement we're going to do. We're going to keep changing stories multiple times, not just twice, like 3 or 4 times. to count something. Also, this is nice because it will introduce another useful tool in counting. So in a way, we've talked about addition, we've talked about multiplication, and we've talked about division, and we've talked about exponentiation as repeated multiplication. Can anyone tell me an operation that we haven't talked about? Subtraction. So how is subtraction useful in counting? So we're going to do an example that will involve subtraction. And this is a kind of fun, complex example. It's not an easy example. So the thing we're actually counting here, in case you want to look, Wikipedia has the proof that I'm describing. We're looking at something called Catalan numbers. Some of you may have seen them. Most of you probably have not, and that's fine. So the nth Catalan number, Cn, is what we're interested in. So I'll tell you a story, the natural story about it. That's kind of a programming story. So, did you guys in 61A have to make a scheme interpreter? Yeah. So if you remember, scheme has a super simple syntax that's also somewhat annoying in that all you have is parentheses. Okay? So imagine you're doing that project and you're having a nightmare. And in your nightmare, all you have are parentheses. Okay? So the question we're going to ask is, how many ways can you have a string of length 2n that consists only of open parens and close parens with balanced parentheses? Okay, so everyone knows, balancing parentheses is the bane of programming existence, and that's why every single one of you has probably programmed in some kind of environment that gives you some help in balancing parentheses. Because trying to keep track of balancing your parentheses in a plain text editor drives you nuts. Okay? So you all hopefully understand the idea of balanced parentheses. So just examples. N equals 1. This is okay. This is bad. Okay? Everyone get this? These are balanced parentheses. These are imbalanced parentheses. However, the following are also bad. This is bad. Both of these are bad. Those are not balanced parentheses. Does everyone understand what we're trying to do? So we have a string. It's going to be length 2n. It's going to have balanced parentheses. Every open paren has to be matched with a closed paren. You can't have any stranded closed parens, right, that aren't matched to a particular open paren. So the question is, how many such strings are there? For n equals 1, there's clearly only one choice, this. Let's think about n equals 2. For n equals 2, there's at least two distinct choices, right? You have this choice, and you have this choice. But other things won't work, because you have to have two opens and two closed to have it balanced. That's the most basic thing. The counts have to match up. But just because the counts match up doesn't make it okay. So, for example, this is not okay. This is bad. This is okay, this is okay, and this is bad. So the question is, how do we count this? And as we count it, we also want to understand how big is this? How many are there? So when you start off and you think, I'm looking at strings of length 2n, how many different strings are there total of length 2n that consist only of open and closed parentheses. Okay? Everyone see the question? Like, how many strings are there that only have open and closed parentheses? Balanced doesn't matter. Well, there's 2 to the 2n. Okay? Note 2 to the 2n strings of open and closed of length 2n. How many are there that have the same number of open and closed parens? Okay, so this is just all strings. So some of these are grotesquely imbalanced because they actually have more open parens in them than closed parens. So now the question is, how many are there? What's the answer here in this box? For strings with exactly n open parens and exactly n closed parens. Okay? How many are there? Anyone? A string of length 2n, it has to have exactly n open parens and exactly n closed parens. How many? Who knows the answer? Raise your hand if you know the answer. Okay, lots of people know the answer. Raise your hand if you're willing to volunteer the answer. Yeah. 2n choose n. Yeah. And so you look at this and you think, this is some thing like this, right? This is 2n factorial divided by n factorial divided by n factorial. So already, I hope you're already a little annoyed. Okay? Because you might be wondering, how big is that? It's certainly smaller than 2 to the 2n. But is it like n plus 3 squared? How big is that number? How big is this number? Because it's a totally different kind of thing, right? It's like this kind of thing filled with factorials, and this is like an exponential. It's kind of hard to compare. So we'll come back to that question in a bit. But you can count this. So now the question is, certainly the number of strings, the nth Catalan number, the number of actually balanced parentheses strings, it has to be less than 2n choose n. But how much less? Right? And what is the actual size? So it turns out that to count the Catalan numbers, there's many different techniques. The Wikipedia page on Catalan numbers has many of them. You can solve it, lots of different ways of solving it. I particularly like this one, which kind of comes from thinking about a story. So if you think about, if you're trying to make balanced strings, you should feel that every time you put an open paren down, so there's kind of like 2 parts to making a balanced string, right? Maybe I'll use this page here. So at the beginning, if you put down open, the first thing has to be an open paren. You know that. So the first thing is an open paren. And now you have a choice. You could choose to put down an open or a closed. But if you put down a closed, you will have no choice at the next time. But if you put down an open, now you have a choice again. You could put down an open or a closed. And after you've put down that open or a closed, you still have another free choice, no matter what you put down. So you should feel intuitively that the more opens you put down, the more freedom you have for a while. Okay, does everyone see this as a kind of intuition about how much? Remember, counting and freedom very closely related. So the question is, can we visualize this, tell a different story for what we want that will help us feel this more acutely? So what we can do is we can say the number of ways that we can have a string of length 2n that's of balanced parentheses is the same as another story. We can think about the integer line, start at 0, and allow ourselves 2 moves. Open paren is going to be the move to the right by 1, and closed paren is going to be the move to the left by 1. And we're going to start here, and our constraint is we have to end here, and this is a forbidden zone. We can't enter it. So what this does, it makes the feeling of freedom more clear. As the further you are from the forbidden zone, the more freedom you have. But if you come all the way back and hit the edge of the forbidden zone, you have to go back that way. Does everyone see this kind of view? It's clearly, this is the same thing now as the nth Catalan number is number of paths on integer lattice starting at 0. So paths length to n. Oh, oops. Move over a little bit. Okay. Starting at 0 that can't go negative. Where your paths are move 1 to the right or 1 to the left. So I've changed the story to this thing. So now I try to visualize this path. So here's a path. Then I go back. Then I go this way. And I go this way. And then I go back and back and back. So that's a possible path, for example. That's a valid. That corresponds to a balanced set of parentheses. Right? That's an open, 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 close, open, open, close, close, close. So when I do this, I feel this is going to get very annoying to draw these lines on top of each other all the time. So I merely feel this annoyance. I am annoyed. I don't want to draw lines on top of each other all the time. Can I change the story again? And so I can. Instead of making open, I'll keep open to be right, but I'll make closed up. Then I won't stop on top of myself, ever. So now what happens is I'm not on the integer lattice there, I'm on the grid. The origin is A. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So if I'm going to look at n equals 6, n equals 6 is 6 right moves and 6 up moves. So if I take 6 right moves and 6 up moves starting at A, where will I end up? I'll end up here at B. So now I want the Catalan number is the number of up right paths starting at A and ending at B that, okay. They can't cross the diagonal. Did everyone see that? Because if I cross the diagonal, I have more ups than I have rights. And that would be an imbalance. Crossing the diagonal is like entering the forbidden zone here. So the forbidden zone is up here. Don't cross diagonal. Is everyone with me so far? So what I've done is I've changed the problem from this scheme-induced nightmare to this walking on this grid and wanting to know how many ways can I start at A, take right and up steps, end up at B, and never enter the forbidden zone. This could all be part of the same nightmare. There could be like lots of parentheses on this side trying to eat you. Like, it doesn't matter, right? So now we have to think. How do we count this? Again, we have the same challenge, right? The amount of freedom we have is different depending on what happened in the past. And it's different. Like if you're hanging around in here, you have lots of choices. But if you're like riding up against the boundary, you have only one choice. You must bounce off the boundary. So at this point, it's useful to make the following observation. Let's call these paths good paths. Okay? Number of good paths. So we can think about it this way. The number of good paths that we have, can we relate the number of good paths to something else? And here, we know we can count some things, right? We know all the different number of strings that go up and right, that get from here to here, all possible paths with n rights and n ups. That's everything on this grid, including paths that enter the forbidden zone. Those are all paths. We can count that. So we can think that good paths are a subset of all paths that excludes bad paths. Okay? So the nth Catalan number, as a result, is going to be equal to 2n choose n minus the number of bad paths. This is minus, okay? Because the sum of the good paths and the bad paths, any path that's not good is bad. So good paths have to be good all the time. Being bad, you just have to be bad once, and you're bad. Okay? So that's the view we're doing here, right? So in a way, all paths are not very constrained, and bad paths have a lot more freedom too. They just have to be bad once. Good paths have to be good all the time. So it's easier to count all paths and bad paths, because both of them have more freedom, than good paths, which are more constrained. You see the idea, the way of thinking here. You want to divide things up, and you want to use this intuition of freedom. Okay? Understanding how much freedom helps you count. So, if you think about the bad paths, what is a bad path? Let's maybe write over here, bad path. What's a bad path? A bad path must enter the forbidden zone. So a path here is it's a sequence of ups and rights. It has n ups and n rights. These are all paths that go from A to B. But what makes it a bad path is that it enters the forbidden zone. Now it could enter the forbidden zone and then leave, and then go back in, and then leave. Right? It can do it many, many times. It doesn't matter. But it has to enter the forbidden zone at least once. Is this clear to everybody? And so now the question is, how do you count these bad paths? So here, there is something which, if I had more time, I can show you how you could discover the way that you could figure out how to count bad paths. So I'll talk about it briefly, and then I'll just tell you the trick. So if you wanted to understand how to count something in today's day and age, when you have a computer, what you can actually do is ask the computer to count the bad paths for you for small numbers. Now, these numbers are going to get enormous fast. So at some point, the computer won't be able to count them anymore. But you can definitely ask the computer to count bad paths for you. You can do it by hand for n equals 2 and 3 and 4. 4? Maybe not 4. Okay? But definitely up to 3, you can do it by hand. It'll take you some time. Just literally enumerate all of them. Like, just carefully enumerate them. Then you can look at those numbers. And if you looked at those numbers, you would notice that these look a lot like something choose something. Okay? It'll turn out. I won't do that now, but it'll turn out. Once you have that, you can then back calculate what could this possibly be. But instead of doing it that way, I will talk about it, with a magical trick. So what I'm going to do is I'm going to use a well-ordering principle-based trick. And that is that good paths, some of them, good paths have to stay in here all the time. Okay? Bad paths start off good, but they could go bad instantly and just go up. Okay? So that's a path that goes bad on like the first move. It was born bad. Okay? But other bad paths, they start off good. And then they go bad. Okay? So the well-ordering principle-based trick says all bad paths have the first time they went bad. There's a first bad move in a bad path. So what happens when the bad path becomes bad? Right? It becomes bad because it crosses the diagonal. Okay? Like, that's what it means to enter the forbidden zone. You cross the diagonal. So let's look at a generic such time for a bad path. So before, this is when it was still good. Then the bad day, when it became bad. And then after. So if it decided to go bad by crossing the KK diagonal position, right? Before, it had taken K right moves and K up moves. K could be 0. That could be in the born path. On the bad day, it has to make an up move. Okay? It made one up move. So afterwards, what does it have to do? It made K rights. It has N rights to make. How many rights does it have to make after? N minus K. It has N ups to make. It made K ups at this point, and it made one more up. So how many ups does it have to make? Yeah. N minus K minus 1 ups. Okay, so this is the nature of a bad path, right? All bad paths, and they were good here, were good. Then, at this point, we no longer care. They're bad forever. So, the question becomes, is there some way we can use this to help us count them? And here, there's a trick. The trick is that what I'm going to do is this trick is inspired by the count and the intermediate value theorem, okay? Which you should remember from calculus, but you'll see why in a moment, okay? So the trick is, what I'm going to do is I'm going to transform a bad path. I will take any bad path, and after the moment it goes bad, I will flip it. I'll turn all of its right moves into up moves, and all of its up moves into right moves. So I'll keep the count, and I'll do an example. Flipped after. So that means that it will now have n minus k minus 1 right moves, and n minus k up moves. So I flip it. I change it. After it goes bad, I change the sense of everything. So if you look at this, like, where does it end up? Okay, where does it end up? It ends up k plus n minus k minus 1 to the right, because that's how many right moves it made. Because it kept this part the same, and then it did this flip part. So it moves n minus k minus 1 plus k to the right, which is the same as saying n minus 1 to the right. And how far up did it go? It moved k plus 1 plus n minus k up, which is the same as n plus 1 up. Which means that all of these flipped bad paths, so I'll write it here, I'll draw there, all flipped bad paths end up at n minus 1 this way, n plus 1 up. Which is to say that all flipped bad paths end up here at point C. Okay? Do people see this? So we'll do an example. Let's do the baddest of bad paths. Okay? The baddest of bad paths goes like this. Okay? It's all closed parens followed by all open parens. Okay? Instead of going inside the zone it's supposed to be, it just goes straight to the forbidden zone, as far in as it can, and then all the way over. Okay? Let's flip it. Flipping it means it gets to make its first bad move itself, so it moved to here. Then we flip it. Flip it means we make it go the rest of these moves, so 1, 2, 3, 4, 5. 5 up moves become 5 right moves. 1, 2, 3, 4, 5. Then its 6 right moves become 6 up moves. 1, 2, 3, 4, 5, 6 ends up at C. So the baddest of bad paths after this flipping operation ends up at C. Let's take another one. Let's say one that's good for a really long time, right? And then it comes all the way to here, and then it goes bad. Okay? So it was doing something nice here. It was very, very conservative. And then it just went bad. Okay? What happens? We flipped this move, which is a right move, to an up move. Again, we end up at C. Do people understand this flipping move? So we take a bad path and we transform it. Now, how many flipped bad paths are there? Is the question. How many flipped bad paths are there? So, I've told you that I can transform any bad path into a flipped bad path. Okay, so can be mapped to a flipped bad path. Now we're counting things. For counting, we care about whether the counts on two sides agree or disagree, whether these maps are invertible or not. If we can show that all bad paths map to a flipped bad path, and in fact every flipped bad path can be mapped back into a bad path, then this is an invertible mapping and the counts will agree. Okay? So let's think about these. Can two different bad paths end up on the same flipped bad path? Okay, that's the question. Can two different bad paths end up on the same flipped bad path? And the answer is no, they can't. Why? Because if they were different during the time that they were good, that part hasn't changed. They cannot be different if they were both bad on the same day on the bad day. Because on the bad day, there's only one thing they could do, cross the diagonal. So if they both had a bad day of k, they can't be different on day k. So the question is, if I have a bad path that has a first bad day of k, if it was different, it'd have to differ in the good part, in which case that part didn't change, or it'd have to be different in the bad part, but the bad part got flipped, and so if it was different, the flip is also different. So that particular case, the two different bad paths can't go to two different flipped bad paths. If they had a different first day that they went bad, well then they're clearly different. The only ones you have to worry about are the ones that go bad on the same day. Okay? So this means that this map is one-to-one. But actually, we didn't even have to do that. What's the easiest way to show a map is invertible? Okay, if you want to show a map is invertible, suppose you want to show that x plus 7 is an invertible map. How would you tell me that, give me a proof that x plus 7 is an invertible map? Yeah. I can actually give you the inverse function. So I can just say y minus 7. If y equals x plus 7, then y minus 7 is x. Like I give you the inverse. You see that? So now, let's think about it. What is the inverse of this flipping operation? Just flip it back. If I take a path, a bad path, and I get a flipped bad path, the flipped bad path still went bad on the same day. Which means if I apply the flipping operation again to this path, I will get back the original path. So this is invertible. Okay, last question. Flipped bad paths are a subset of all paths with n minus 1 rights and n plus 1 ups that go from A to C. Right? Oops, that's clear, right? If I have a flipped bad path, it starts at A and ends at C. It has n minus 1 rights and n plus 1 ups. So all flipped paths are going to be some path that starts at A and ends at C. Is that clear? So now here's the question. Are there any paths that go from A to C that are not flipped bad paths? Okay, if you want to show if we know how to count all the paths that go from A to C, like that's going to be easy. Yeah. Exactly. By the intermediate value theorem, we start on this side of this line, we end on that side of the line, we have to cross the line. Okay? So all paths that go from A to C have to cross that line. They can try to be good all they want, right? At some point, they have to go bad. So all flip bad paths, they aren't just a subset, they are the same as. And now, how many paths are there that go from A to C? Well, I simply have to choose of 2n positions, n minus 1 positions, for the rights. So now I know the nth Catalan number. Number of bad paths, this is the same as 2n choose n minus 2n choose n minus 1. Oops. So, this is an example of a count. So, notice I could have just as well written 2n choose n plus 1. Like 2n choose n minus 1 is the same as 2n choose n plus 1. They're the same expression. I just wrote 2n minus 1. It doesn't make a difference which one I write. So this is an example of counting. So this is a little bit harder than I expect you guys to be able to do on your own, because you had to, there was a couple of steps, but there was many different moves we made, right? We started with this nightmare about parentheses. We went to these paths. We said the paths on the line were too annoying, so we went to paths on this grid. Then we said we have this forbidden zone. We said, okay, to count the good paths, let's divide between all paths and bad paths. Then for bad paths, we connected them to flipped bad paths, which are paths from A to C. And to get the final count, we counted these different things. This is combinatorial. This is how combinatorial proofs work. This is combinatorial thinking. Yeah. Yeah. So the question was, how would you have discovered the flipping? Okay? What you would have discovered is, as you were counting using the computer, the bad paths, you would have seen it was 2n choose n minus 1. Okay? That number would have come out. Because you would get n equals 2, n equals 3. These would be numbers you would recognize, because remember, these are binomial coefficients, right? And so the binomial coefficients, they appear in Pascal's triangle, which means they're familiar to you. You'll see them. You'll go, wait, I know you. You're a number I've seen before. So once you recognize just from experiments that you have this, you would look at this figure and ask, what corresponds to 2n choose n minus 1? Right? And you say, maybe I can get the story to work if I just choose n minus 1 right path. Right. And that would give you the point C. Then you would conjecture that the number of bad paths should be the same as all paths from A to C. And then you would say, I have to cross the boundary to get there. Then you'd go, wait, but this isn't quite the same. Then you say, I can flip after the boundary and get here. And then you get it backwards. This is how you can discover it. But that's the level of discovery. So again, what matters here, for most people, everything I described is something you can do. However, most people at this stage will simply freak out before they get that far. Just go, I give up. Okay? But you just have to be patient and not freak out. And then it becomes possible. But we don't expect you to be able to make a count. Now that we've taught you this, we can make you do this kind of thing with the flipping or something, but we can't expect you to do something of the same complexity. But I wanted to show you an example that was more involved. It's not in the notes, but it's in Wikipedia. This exact proof is in Wikipedia. So now that we have this, we have the nth Catalan number, we have this question, which is, how big is this? 2n choose n minus 2n choose n minus 1. Is this a big number? Is this a small number? How big is this? So, to figure this out, we can just ask this question. 2n choose n minus 2n choose n minus 1. How big is it? First thing you do is try to simplify. So you take this thing, because you might think, this is like 2n choose n things, 2n choose n minus 1 things. Maybe these are pretty close to each other, right? And they'll most things will cancel out. So you look at this and you go, okay, let's just write it out. 2n factorial, n factorial, n factorial, minus 2n factorial, n plus 1 factorial, n minus 1 factorial. Ugh, common denominators, right? Multiply top and bottom by n here will get me something with an n plus 1 factorial, n factorial, right? So if I multiply top and bottom by n, I get n plus 1 in this case, sorry. I get an n plus 1 2n factorial. And then I get a minus. So here, to get the n, I need to multiply top and bottom by n. N times 2n factorial. I get some cancellation. N's cancel, but I still have this 1. So this thing is 2n factorial divided by n factorial times n plus 1, which is the same as 1 over n plus 1, 2n choose n. So this is interesting. The nth Catalan number, the number of strings that are balanced parentheses, is just a factor of n plus 1 smaller than all strings with n open parens and n closed parens. Just a factor of n smaller. So the question next becomes, is a factor of n a big thing or a small thing? So in this case, I want to introduce the last topic that I want to put into scope for today, which is Stirling's approximation, which is just an amazing thing. Okay? So you look at this and you say, how big is 1 over n plus 1 divided compared to 2n choose n? So then you have to confront the fact that factorials are hard to work with in terms of understanding how big they are. They're big. You know they're big. Okay? But you don't know how big. So it turns out there's something called Stirling's approximation, which is a way of approximate thinking that says n factorial is approximately equal to square root 2 pi n. So tell me if people have seen this before. 2 pi n divided by e to the n. So who's seen this before? Stirling's approximation. Raise your hand. It's sometimes a standard topic, sometimes it's not. So who's seen it before, Stirling's approximation? A couple of you. Who has never seen this before? That's fine. So you look at this and you go, what the heck is going on? Right? N factorial is the most wholesome thing there can be. Right? It's like a whole number times another whole number. It's not even a strange whole number. It's like the next number. Right? And times another whole number. You just take a bunch of whole numbers right next to each other and multiply them together, and out comes this party which has the diagonal of a square, square root of 2, the ratio of a circumference to a diameter, the pi, and the base of irrational number of a natural logarithm is e. So these 3 irrational numbers crash the party, right? Just show up. And you're like, what? How what? Okay? So it's actually a really good exercise to plot this and see just how good of an approximation this is. It's like amazingly good. It also turns out to be super useful. We will make you on the homework derive this part of it and this part of it, but not the square root of 2 pi part. So it turns out, so to understand the square, so you look at this collection at this party, you know their friend is somewhere. Okay? Who's their friend? J, the imaginary number. Right? It turns out the proofs of why you get the 2 pi involves complex analysis. Right? So these three are at the party, but their friend is like driving the car, right? So, but these guys you can get using calculus and understanding Riemann integration and its connection to the trapezoid rule for integration, which is all topics you've seen before, but you can use that to derive this scaling, and we'll make you do it on the homework to make sure you understand. But once you have the Stirling's approximation, you can then, and we'll do it briefly next time, you can understand just how big this is and this is by grinding out Stirling's approximation on it. Okay, so yeah, next time we'll do this. I have office hours now. We will continue with closing off counting and more stuff later.